Hey everybody, welcome. Yeah, so before we get started, university asked me to share this with all of you. I hope you've been getting emails about this as well. You should have all been receiving some emails about some of the vaccination clinics that are on campus as well as all around the community. So you're all eligible. Yeah, so if anybody's having any difficulty, I'm not a vaccination expert, but I'm happy to help you. I don't know how difficult it is finding appointments nowadays, but there's also a link on the bottom, the links together that you can go to get some information about that. So hopefully everyone that is able to get vaccinated can get vaccinated, and we'll have a nice healthy campus next semester. That's the goal. Okay, so any questions about anything before we get started today? The plan today is to work on the next worksheet, worksheet 20, which is dealing with bijectivity and surjectivity. So we're dealing with functions. So this homework assignment that you guys have due right after the break covers everything up to including what we're going to talk about today. So that homework, again, is due the Monday we get back from the break. We don't have class next week. And then after the break, we'll talk about inverse functions and cardinality of sets. And then that's it. Sadly, that's the end of the line for us in Math 3000. So we're almost getting there. Okay, let me open up the worksheet then. The worksheet is up in Canvas. If anybody is having trouble getting it, just you can just chat me and I can upload it in the chat as well. Okay, and everybody can see this, I hope. Can you guys see my screen? Good. Okay, so far things are working today. Good. Okay, so what you guys kind of reviewed for class today with the video was just some of the stuff we talked about earlier in the semester about what is a function, domain, codomain, range, injectivity. So this was stuff that we talked about, just prior to exam 1. In particular, when we want to show that something is one-to-one, or injective, we did some proofs with that. And the definition is over here. So one way to prove it is to do it directly and to say, let's assume we have two different inputs, then let's show they give us two different outputs. With statements that involve not equal to, we've seen sometimes it's easier to start a proof assuming something is equal as opposed to not equal. So in some cases, it might be useful to do a contrapositive proof for this. Meaning you suppose the negation of the conclusion. So you suppose that f of x is equal to f of y, and then you hope to show that that implies the inputs were equal to each other. So those were proof techniques that we used to prove things are injective. And we'll go through a bunch of those today. But any questions about that material? Okay, so then what I want to add to that today is another nice property about functions, which is if they are surjective or onto. Okay, so we use these terms interchangeably. And what it means real briefly to be surjective is that the codomain is equal to the range, right? So everything in the codomain has something in the domain which is mapped to it. Yeah, okay. And so if a function satisfies both of those properties, then we call that function bijective. That's definition 3 down here. So when we want to prove whether or not a function is surjective, what we need to show is that given any element in the range, oh no, I'm hitting my iPad, but you guys can't see it. Some reason they updated this app, and there's a presentation mode and regular mode, and the presentation mode doesn't seem to work with Zoom very well anymore. Okay, I'm sorry. Anyway, that's my problem. Okay, so if we want to prove that something is injective, okay, sorry, we have a slight delay here. There we go. Then what we want to show is for any thing in the codomain, which is what B is representing, for any element in the codomain, there exists something in the domain which is mapped to it. So in other words, everything is in the range. And we would call this thing over here a pre-image. Sorry, yeah, the pre-image of Y. Since it is the element that gets mapped to Y. So it is the image of X, or excuse me, it is the thing that gets mapped to Y. And so if we want to prove that a function is surjective, then what we need to do is take any element in the codomain and show that there exists an element in the domain that gets mapped to it. Okay, so any questions? Okay, so let's kind of consider this example over here. So let's consider the function, and this is the absolute value function, but we're not defining it on the real numbers. We're defining this on the integers. So first thing to check is, okay, this is a function given in input. We get only one thing out, so it's a function. We have the domain is Z, the codomain is Z, and the question is, well, what's the range? So what do you guys think about this function and whether or not it would be injective?
I don't think it's. Wait, are you going to do the voting thing, or are you asking for?
No, I'm just asking for anybody to share their thoughts here. So absolute value function defined on integers. Do you think that's injective or not? What do you?
It's not one-to-one.
Okay, why not, if you don't mind?
There, like for example, if the absolute value of 1 is equal to the absolute value of -1, so they both there's like it is expressed twice basically.
Yeah, so if we want to prove that something doesn't satisfy this property or any property, right, we just need to provide one counter example. So let's consider this thing, and when we're kind of writing out mathematical proofs, it's good maybe not to just start your sentence with some notation. So rather than just throw somebody in to this, just putting a couple of words before that sometimes makes it a little bit nicer. So the function f of a equals a is not injective. And we'll prove this using a counter example. So we can consider a, which is equal to 1. So this is what Ken was suggesting. And we'll consider b, which is -1. These are two integers that are not equal to each other. Since a is not equal to b, but f of a equals f of b, the function is not injective. Any questions? Okay, so it's a function. Don't hold it against it that it's not injective. It's still a function. We still have one input going to one output. So it does satisfy that, but it's just that for some outputs, we have more than one input, which is being mapped to it. What do you guys think about surjectivity? So here we want to think about, right, the codomain. And if every integer is in the output of this function, is in the range of this function, then it would be surjective. If we can find one thing in the codomain, if we can find one integer which is not in the range, then we've got a counterexample. So anyone think of a counterexample for this? What's something that would be in the codomain which would not be in the range? Yeah, thank you. So I got a comment in. -1 is in the codomain, but not in the range. Exactly. Yep. Thank you for that. Yep. So let's consider -1, which is in the integers, which equals the codomain, excuse me, of this function. So there's no integer, there's no input a, which when I take the absolute value of it is going to give me -1. So this is a function. I could just say, like, after we verify that it's not injective, that would be enough to prove that it's not bijective, right? So in order for a function to be bijective, it needs to satisfy both. So this would be a case where this one satisfies neither of these properties. Any questions? Okay, I'm going to open up a poll for this one. And the question is, what, I'm not asking for like formal proofs here because it's just a poll, A, B, C, or D. But what do you think about h of x equals x squared? Injective, but not surjective, surjective, not injective, both or neither? Okay, I think we got one more person that hasn't gotten their vote in. Perfect. Thank you. Okay, so here were the results. We got 7 people outside of Lindsay and myself. Yes, we had 3 say surjective, but not injective. 2 for a bijective. 2 said neither. So I'm thinking that these might be terms that you've heard before. One-to-one, I'm sure that you have probably come across that terminology at some point. And so I don't want to kind of suspend any sort of mathematics that we've previously learned. When I think about this, I think about that, right? That's not a smile, that's a graph there. So I think about this. And I think about, okay, I've learned about functions and I've learned about some of these properties of functions, at least informally. Whoops. So here's kind of the graph of h of x equals x squared. And we can use graphs to confirm whether or not this seems to be injective as well as surjective, right? And so for it to be injective, it needs to pass the horizontal line test. Oh, excuse me, the vertical line test. No, I was right the first time. Horizontal line test. Vertical line test, right? That's how we check for a function. So what I mean by a horizontal line test is we can, if every horizontal line that we draw through the graph intersects it in one place, then it's one-to-one. And in this point, we can see that there certainly are some output values some constant here that have multiple inputs that get sent to it. And that's going to be a problem. So, this is fine, but when we prove things, we can't just draw a picture. So if you want to use a graph, you can draw the graph and then make some comments about the graph and how that connects back to these things. That's fine, but just keep in mind, just drawing the graph and saying it fails the horizontal line test is not a formal proof. It certainly is a good way to kind of justify which way you're leaning. So here we're going to say, let me just say it like this. So remember, when we want to disprove something, we just need a counterexample. I need to provide, like we did in the previous example, two different inputs that get sent to the same output. Anyone have a suggestion here?
-1 and 1.
Yeah, we can use the same ones again. That's right. That's really all we need to say about that. So that is actually a formal disproof, more so than like the graph above. But certainly we could use the graph above to identify the counterexample. So so there were a couple people that thought it was bijective. So just this would have ruled it out at this point, right? So since it's not injective, this function can't be bijective. Any questions? And in order for this to be onto, that means every single thing in the codomain would have to be in the range. So, right, when we're thinking about graphs of things, we think about the output on the vertical axis, right? So inputs on X, outputs on the vertical axis. And so in order for this to be a surjective, that would mean the graph would have to intersect every horizontal line in at least one place, right? That any horizontal line that I draw corresponds to an output. So here's something which is indeed in the range, because when I draw a line through that y value, I hit the graph. Down here, right, if I draw this horizontal line, I'm not intersecting the graph anywhere. So what this is telling me is there are some outputs that don't have any input value being mapped to it. And if you think about what happens when you square numbers, they no longer can you get a negative number, right? So there's no way that I can plug in an input for x and get like -5 out of this function, because when I square any number, I'm going to get something non-negative. So here, the range of this function, we called it h. Right? It's all non-negative numbers. Okay, which is not equal to the codomain, which is the set of all real numbers. So one way to prove this would be you could graph it and then comment on the graph like I've been doing, but you would want to write that out clearly. We're going to prove this also by counterexample. So let's consider something like -1. Okay, so this tells us H is not surjective.
If the question instead said, let H be real mapping to positive real, would it then be surjective?
If we change the codomain and instead, let me redefine this. So I'll just say, like, if we had some function g, which was going from R, into, let's say, this. That would be surjective, right? It still would not be injective because we still have this issue with positive x is negative x going to the same thing, but that would fix it. And to kind of take it to the extreme, right, we could go even further and say, well, if I had a function that looked like this, where h of x equals x squared, okay, well, now that is a bijective function on those restricted domains and codomains, yeah. And this is something we do in mathematics when we have something which is not invertible, but we want to make it invertible, then we just restrict domains and ranges. That happens with like the trig functions, for example. Yeah, good question. Any other questions? Let's take another poll for question C, for part C of this one. Do you think this function j, which is the x cubed, is which properties do you think it might satisfy? Okay, let's see. So we've got everybody in. We've got 6 votes for bijective and 1 vote for injective, but not surjective. So everybody thought this was injective, in other words, and that is true. This is injective. And again, you know, I think a good starting point for these, if you're having trouble with that, would be, well, hopefully we've got the graph of x cubed also something that's stored away pretty handy. That's not the best looking graph of it, but it should look like a chair kind of thing. Sorry, my hand keeps slipping off my iPad. There we go. And so here, if we do draw horizontal line anywhere, we can kind of see that we're hitting the graph once and exactly once for every horizontal line that we draw. So that's a good sign. So we're hitting it once, it means it's 1-to-1. Since every horizontal line hits the graph someplace, that tells me that everything in the codomain should have some pre-image which is mapped to it. Well, let's prove it. So this one is both of those properties. Okay, so given any output value, anything in the codomain, I can find something in the domain which is mapped to it. That's what's going on there. So this function is bijective, and let's prove this. And so you've got some of these on your homework. So in order to prove that something is bijective, right, then there's two things that we need to show: the injective property and the surjective property. So like, you know, some of the other proofs that we've been doing, it's good to just label, here I'm doing the injective part, here I'm going to do the surjective part. And so to prove something is injective, just recall that what that means is if x is not equal to y, that should imply f of x is not equal to f of y, or if f of x equals f of y, that should imply that x is equal to y, right? So we can do the direct or contrapositive, and I'm gonna choose to do the contrapositive proof here. Okay, and so all these little things are really helpful actually for someone trying to get in your frame of mind and follow what you're doing. So let's assume we need to tell people what x and y are, if I'm going to use them. So let's say we've got two things in the real numbers. And right, just by saying x and y in an R, we're not claiming they're different or equal. They're any two things, right? They could be equal or not equal. And what we're going to show is if their outputs are equal, then x and y have to be the same thing. So if we know that f of x is equal, here we don't have f, sorry, we have j's. Okay, this tells us that x cubed would equal y cubed by definition of the map J. And then how can I go from here to show that this would imply that x is equal to y? Yeah, thank you. Take the cube root, take the third root of both sides, right? So we would have an issue in the previous example with the square root one, because when I take the square root of both sides, we have a positive and a negative option. So there could be possibly two things when I square them that give me the same thing. With odd powers, that's not the case. So so taking the cube root of both sides, so that's our contrapositive proof of injectiveness. So when we're dealing with our more standard functions, like single variable functions from R into R, these things typically are like algebra problems. Setting two things equal to each other and then showing that their inputs are equal to each other. Were there any questions about the injective part of that proof? Okay, so if we want to prove that something is surjective, then we pick an arbitrary element in the codomain. And here, I'm just indicating that R is the codomain here because there is some, I suppose, there could be some ambiguity because the domain and the codomain are the same. So this might just help tell the reader, here's what I'm doing. I'm picking an arbitrary thing in the codomain of this function. I'm going to call it Z. And we want to find what input is going to get mapped to Z. So let me ask you guys this. If I want the output of something to be Z, the output of this function to equal Z, what would have to go inside that function? And you think of something that when I plug in the input into this function and cube it, I wind up with just Z.
1.
So if I plug in 1, I'm going to get 1 out. So I want to think about what thing do I plug in here? It's not going to be a number, right? It might be some expression that depends on Z. So we want to show that we can get an arbitrary thing out, any arbitrary thing out.
Cube root of Z?
Yeah, so if I plug in the cube root of Z into that function, cubing it will give me Z. So what I want to show is that there is a pre-image in the domain that is mapped to Z. Oops. Okay, so here I just want to make this distinction about again, because our domain and our codomain are both real numbers. So I'm saying, okay, let me pick something that's in the codomain. Here's something which is in the domain. Any number, any real number has a defined cube root. We're not going to get some complex thing when I take a cube root. So this tells me now if I take j of the cube root of Z, this tells me that Z is in the range of J. So anything that's in the codomain of J is in the range of J, thus J is surjective. And this proves bijective, right? Now that we've got both injective and surjective. And what we'll see shortly is that these functions that are injective, surjective, bijective functions are particularly nice because they have inverses. Any questions? Okay, I'm gonna do we'll do one more polling one together, and then it'll be time to have you guys practice a couple of these. But let's think about D, which is this function k of x is x cubed minus x Do you think that is injective, bijective, or neither? Okay, got one last vote out there. If you want to, oh, perfect. Thank you. Okay, here are the results. Nobody thought this is bijective. It is not bijective. And so 4 people said neither, and then we have roughly the other half thinking it's one but not the other. And so here's a case where sketching the graph, maybe it's not so easy to draw this graph. I don't know. But let's see what you guys were thinking about this one. So here, first thing is this function is not injective. And to prove that, we just need to provide one counterexample. I'm not sharing the results. Here are the results, in case you guys don't believe me. So what is, can anyone think of a counterexample for why this function is not injective? Can you think of 2 inputs that get mapped to the same output?
One and zero.
Yeah, so I'm getting a lot of 1 and 0. Yep, perfect. Those are nice because when we plug in 1 and 0, they both give me a 0, right? Let's consider, I think -1 might work as well, right? -1 cubed is yep, and -1 would work too, but we just need 2. So we'll take an x is equal to 1 and y is equal to 0. Okay, those are different values, but f of x and y both give us 0. That's really it. You know, and don't just say like this, don't just stop with saying like, here's the thing, but actually just go through and tell the reader, like, here's what I checked to verify that. Okay, so next up would be surjectivity. Any questions about that? So K is surjective. So I think we had 2 people say it's going to be a surjective, but not injective. So this is actually surjective. Then when see maybe like an informal justification about how you thought about that.
I thought of it as like you have x cubed, which is, as we proved earlier, was surjective, and x is surjective as well. So I assume that if you combine the 2, it's still surjective.
Very interesting thing here. Is the difference of 2 surjective functions surjective? And the answer is not always, no. So you want to be careful about that, right? We have functions that satisfy certain properties, and then we'll think about, well, what happens when we add them or subtract them or compose them is what we'll talk about next time, what happens with those things. And, you know, for example, f of x equals x is surjective, g of x is equal to x plus 1, that's another surjective function. But if I take f minus g, right, I just get the function minus 1, which would not be surjective. Yeah. So just watch out for that. But you're right. If we can kind of consider what is going on with x cubed, right? So what we know about polynomials is that their long-term behavior is determined by the term with the highest power, right? The leading term. And so in particular, if I take the limit as x goes to infinity of this function, what would I get?
Positive infinity.
Yeah, this is, at least I guess it does not exist, but it's going to head off to positive infinity. Yeah. And if we take the limit as x goes to minus infinity, this is maybe equaling minus infinity is not the right thing here, but right, it approaches minus infinity is what we usually say. So this means we've got a function doing this on one end and doing that on the other end. And in between, we know that polynomials are continuous. So, right, it can do a whole bunch of stuff in between, but at some point it's going to have to connect those two arrows, which go off in opposite directions forever. So this is surjective, and that's going to be true for any odd degree polynomial because of this behavior over here. So what the argument that I kind of made with that, drawing that thing is really what's called the intermediate value theorem, which says, okay, if a function is continuous and I know it has this value and that value, then it has to take every value in between. Yeah, so let's write that up. So here, we're not going to necessarily prove, well, yeah, okay. Let's we can do this really precisely. Let's consider something in the codomain R. Then we can say since the limit of this function as x goes to infinity approaches infinity, and the limit as x goes to negative infinity of k of x approaches minus infinity, then by the intermediate value theorem, this tells us that any number z in my codomain, which falls between minus infinity and infinity, that there has to exist some input with function was k, so that when I evaluate k at this input, we get z. And I left out one kind of point that we should let the reader know, and that is if we're going to apply the intermediate value theorem, the function needs to be continuous. So we didn't make that comment over here, but it's worth noting someplace. We could say that this function is a polynomial, so it's continuous. Because we need that assumption to use the intermediate value theorem. So we've seen examples that are injective, not surjective, so you can have any, there's no relation between if you're injective, you have to be surjective or vice versa. So you can be injective, not surjective, surjective, not injective. You can be neither of these things, both of them. Okay, so I think it's time to try and think about some of these in groups. So I think as you're maybe talking about them in groups, I would just start by thinking about it informally, like, hey, what do we all think? And then make sure you're on the same page before you try and like get into the details about how are we going to prove it does or doesn't satisfy this property. But for I just want to make sure that the maps, the functions themselves are clear. So here we're thinking about the power set of x, okay, and x is some set of we can think of them as some set of numbers. So this subscript or superscript, excuse me, means we're going to just deal with finite subsets. So even if x is an infinite set of like all even integers or something like that, we're going to think about our input here as all of the finite subsets of x. That's what these power sets would be. And this map, so we're thinking about x here as real numbers. So I could have an element, some set A, right, which contains some finite amount of real numbers. I've just picked weird ones because they don't have to be integers here, right? They can be any real number. And what this map is doing, this map Q would map this to 3 pi e squared, right? You just take the product of those three things. And since we have a finite number of elements, right, the product is going to be a well-defined product of a finite number of things. So we have our codomain is R. We're mapping to the real numbers. The domain here is different. It's finite subsets of R. So the question is this map, which takes a set and maps it to its product. Do you think that's injective, surjective? And down in F, I think that's a little bit, that should be a clearer definition. I think when we deal with power sets, sometimes it's a little bit hard to wrap our head around what the function is doing. F is just the floor function. So it's different than rounding. It's just saying we have some number, we just truncate its decimals and think about the next integer, which is just below it. Okay, so make sense what you guys can discuss in your groups. All right. All right, so I'm going to set up 2 rooms. So I was just jotting notes down from what the group was talking about. They had the whiteboard going, so please correct me if I have something wrong here. But for the power set one, we came up with, or they came up with, not being injective, but it is being surjective. And yeah, this is kind of a weird thing. We're thinking about power sets of the real numbers. Real numbers are infinite, so these could be infinitely large sets, in which case the product wouldn't make sense. So we're just going to restrict the domain to be finite subsets of the real numbers. And so, for example, we could have weird sets like A up there. And yeah, so the idea was it's kind of thinking about, right, there are different ways that you could write things that multiply to certain numbers. So yeah, here was the counterexample that group I was with came up with. Yeah, you could probably also just there are tons of, right, there's tons and tons of sets that would have a product of 2. You could think of you can come up with all sorts of crazy ones as well, right? Since we're dealing with real numbers. And then for the surjective part, that was a little bit trickier, I guess. But the idea was we want to show that any real number in the codomain is going to have some set that has a product equal to that. And so one thing that was that might be helpful is if you're kind of stuck thinking about this. Usually we can do these things by constructing a pre-image. You can say, here's a general output. Here's what the pre-image in general would be. And if it's hard to generalize that, you can kind of just like pick a random thing in the codomain of this function, and then think about what is a set that would have an output of 3. And I think the one that we kind of came up with was like, okay, if you take the set 1, 3, its product is going to be 3. So this is kind of just some scratch work. And there was nothing special about 3. So sometimes if you get stuck, you can just pick a specific example and then see how that might be able to be generalized. So given any real number z, right, there's some set 1z whose product is going to give us z. Any questions about that? Okay. And do you guys not get to the floor function? I guess not yet. Okay. Sorry. So were there any questions about either of these statements? Okay. So then with the floor function, this is this function that truncates the decimals. So it is gonna maps any number to the integer, the closest integer that is less than it. So f of 2 is 2, f of 3.14 is 3, and so on. So I think we kind of left things noting that it is not going to be injective because, for example, 2.1 and 2.2, they would both get mapped to 2. And kind of looking at this gives us a way of seeing that, like, right, we're considering the codomain of this function to be integers. And when this map is going to take any integer to itself, right? So that sets us up for this to be surjective. I don't think we did that part. Well, I don't know. I closed the room by accident when we got to that point. But here we can pick some constant in the integers. We got a little bit of a delay. There we go. So basically, we can show that any integer has some pre-image, right, that gets mapped to it, basically itself. There are tons of other things that get mapped to C too, right? But we just need to give one of them. So the most obvious one would be like the integer itself. And here we're okay because integers are in the real number. So this thing is indeed in as well. It's going to be in the codomain, or excuse me, it's going to be in the domain. So we can plug this into the function and then get that output. So yeah, so there was a question, I think, if I'm understanding it correctly, was if this function were defined like this, where we're going to take x and map it to the floor of x. And if we were considering the codomain to be all of the real numbers, then it would not be surjective. That's right. It wouldn't be injective, and now it's no longer surjective because I can't get something like 2.1 out of that function. Yeah. Okay. So let's, are there any questions? So let me do one that I think might help with what you guys might have to do on your homework. So let me just add a page here. Give you some idea. So on homework, you don't have this exact one, but let me consider function that looks like this. And you guys have to show or think about some rational function like this and think about whether it's injective or surjective. And kind of the first point here is that this is not actually even a function, because every input doesn't have an output as it stands now. So I'm going to pop out 3. Okay, now it's a function, or not 3, but -3. So that notation means all of the real numbers excluding the number -3. So if we tweak that domain to R minus -3, that makes it a function. Every input has an output. So if we want to prove that this is injective, then I would like to show, okay, here are 2 different outputs. They give me here are 2 different inputs. They give me 2 different outputs. Or you can do the contrapositive. If 2 inputs give me the same output, then those inputs have to be equal to each other. And so it's going to be weird. If I think about this, let me just kind of write up. Right, you can think about, okay, here's f of x, here's f of y. It's possible that they can equal each other, even though the numerators and the denominators are all not equal to each other, right? Like I could have 6/3 and 3, and maybe they still give me the same, or 2, and maybe they still give me the same output. So here's kind of a little tip that might help with this. I'm going to rewrite this fraction in the following way. going to do some polynomial division here. So x plus 3, for those that might not have seen this for a little bit, right? I can say, okay, x plus 3 goes into 4x minus 1 4 times. So when I cancel that out, I get a minus 13 over here. So what this means is I can rewrite this quotient as 4 plus minus 13 over x plus 3. It's like doing a, breaking that fraction up. So it's the equivalent of saying like 3/2 is the same thing as 1 plus 1/2, right? That's kind of the equivalent of what we're doing here. And so now when I have it in this form, this might make it a little bit easier to show why two different inputs, if they give me the same output, they have to be equal to each other. I'll just say up here, the algebra would be messy trying to work with those two expressions up there, trying to show that if I set those two things equal to each other, why is that going to imply that x has to equal y? So sorry, I think we're just out of time, but so if you need to run, no worries, but I'll wrap this up and put up the video on there. So this will help a bit on your homework if you get stuck on that. So I'm going to rewrite this function in the following way. And so now when we're going to prove that it is injective, let's take two things in our domain with f of x equals f of y. Okay, and now the advantage is, again, if I just set this equal to that, we've got these two fractions, and the algebra is not going to, it's not going to be easy to show why x is going to have to equal y. But if I've got it written this way, if I have it like this, now it is a little bit easier to show why x is going to have to equal y, right? Now the algebra that I can do to both sides is a little bit clearer. It's not so clear up here. What would I do to start solving for x or start solving for y? But with this equation down here, right, we can subtract 4 from both sides. And then, from here, you can see the algebra that goes from there, right? We could divide both sides by minus 13. And so if 1 over x plus 3 equals 1 over y plus 3, this tells us that x plus 3 should equal y plus 3. And therefore, x is equal to y. So the hint there is you might not think about dividing these things and rewriting the fraction this way, but that makes the algebra a little bit easier when we're trying to match up our x's and our y's. Any questions? And if you've got a couple more minutes, I can also give you a hint for the surjective part. Again, if you need to run, go for it. I'll be recording this anyway. It won't take long if you've got just a minute. So we're defining this function f of x. What was it? X plus 4x minus 1 over x plus 3. And so if we want to try and show whether or not f is surjective, going this way, it doesn't help or hurt using this alternate representation that we had over there. I think we can work with this function, this version of the function here. So we could say, well, let's take something which is in the codomain. Then we'd like to show, okay, what is the x value that's going to give me this output of C? So maybe I'll just say I can do some algebra here. To figure out what the value of x would be. Right, what we're trying to do is find the x value, right? So I'm grouping my x's together. So I found if I let x equal this, when I plug it into the function, the output is going to be C. We have a problem here. That is as long as C is not equal to 4, right? If C is equal to 4, we have a problem. And in fact, there's no way that that is ever going to equal 4. If you look at the top, I mean, I have a 4x up here and I have an x on the bottom. So we're actually missing something in the range. So that's why the function that you have on your homework assignment also pops something out of the codomain. And so if I remove 4 from the codomain, now this is surjective. So as long as that 4 is removed, now it is going to be surjective. And we just did some scratch work over here to figure out what the x value would be. So to prove this, I don't need all of that. So here we're safe avoiding this fact about being 4, because if we assume that C is in the codomain of F, that means we don't have to worry about getting the 0 in the denominator now. Okay, sorry for keeping you guys over, but hopefully that maybe saves you a couple minutes while you're working on your homework. Okay, well, have a nice break, everybody. Have a nice spring break. If you have any questions over the break, don't hesitate to ask. I'll be around. But otherwise, if you just want to take a break from me, that's fine. Have a good week, and I'll see you guys, yeah, in like a week and a half after the break.
Thank
Take
you.
care.